Here we have a ladder whose length L is 12 meters and whose mass M is 45 kilograms rests against a wall. Its upper end is a distance h of 9.3 meters above the ground. The center of gravity of the ladder is 1/3 of the way up the ladder. A firefighter whose mass M is 72 kilograms climbs halfway up the ladder. Assume that the wall, but not the ground, is frictionless. What forces are exerted on the ladder by the wall and by the ground? First we draw an FBD for this system and we see the forces that are present. First is the force by the wall that is perpendicular to its surface, and we could say that this is also the normal force from that wall. The angle between this force and the ladder is theta, which is determined by symmetry or geometry. We note that this wall is smooth or frictionless, which suggests that there would be no force countering the slide along the wall or y-axis in this part. The next two are the weights, the weight by the person or firefighter and the weight of the ladder with an angle phi with respect to the ladder. The next one is the force exerted by the ground surface on the ladder at point O, which we could say is the normal force from this second surface. The last one is the friction force by the ground surface, which counters the slipping direction of the ladder, preventing it from moving. So the system is in equilibrium, and we could use the conditions of equilibrium to solve for force exerted by the wall onto the ladder. The next step is that we use the second condition for equilibrium, which is that the net torque is equal to 0. Here we identify the forces that could cause the motion of the body to rotate clockwise and counterclockwise if it is allowed to move freely with respect to its axis of rotation positioned at point origin O. For the first force or force exerted by the wall, it would cause the body to rotate clockwise. For the weights WP and WL, they would cause the body to rotate counterclockwise, and for the forces the normal force and friction whose line of action intersects the point of rotation, they both do not cause movement, so they are both 0. So we see that the function is simplified further and we rearrange it to obtain an expression for the force exerted by the wall. We see that we need to solve the angles or the sign of the angles to get the value of the force. To solve for the angles or sign of the angles, we go back to the figure and we see that the angles theta and phi form a right triangle, which we write about in terms of its sine function. First, for theta, it's simply sine theta is equal to h over L. For phi, it is sine phi is equal to a over L. So, we encounter another problem since a is an unknown and we need to get a better expression for it. Applying the Pythagorean theorem, we see that L squared is equal to a squared plus h squared. Solving for a is equal to the square root of L squared minus h squared. Substituting this to our sine phi function, we get that sine phi is equal to the square root of the difference of square of L and h over the quantity L. Now we can stop here and substitute these values, but we can also simplify the ratio of the sine functions that is present in the equation for force exerted by the wall. The sine ratio of phi over theta is done by substituting the values of the individual sine of each angle, and we get that it is equal to the square root of the difference of the squared L and G over the quantity h. We then substitute this back to expression for Fw. Substituting the obtained function from the ratio of sine phi over sine theta, we have now an equation that we can use to determine the value of Fw. We then substitute the values from the given and we see that the force exerted by the wall is around 407 newtons.